Section 1.4 is on approximate linear relationships. Definition: if the points in a scattergram of the data lie close to or on the line, we see the variables are approximately linear related. In example 1, we have the amount of money that Americans spend on cell phone services is growing. Let m equal f of t be the amount of money spent on cell phone services in years since 2000. So t is going to be the number of years since 2000, and m is going to be the annual amount of money spent on cell phone services. So what I have here is a list of years. I need a list of t values. T values are years since 2000, so my t values will start at 1 for 2001, 2, 3, 4, 5, 6, and 7. 2007 is 7 years since 2000. So these are going to be my t values, the values of my independent variable, and the values for m, the dependent variable, will be these values listed in the second column right here, the amount of money. So what I want to do first is make a scattergram. So I'm going to have my independent variable t along the horizontal axis. And actually the scattergram has been created. I just need to go ahead and label that. So I'm going to have t along the horizontal axis and m along the vertical axis. Now I need to figure out what scale was used here. It's kind of easy to find the scale for t because the values for t are 1 through 7. And it looks like that corresponds with what we have right here, 1 through 7. So let's label these. Now let's look at the values for m. The values for m are going to range between 200 and 600. So it looks like if I count these by 100, this would put us around 200, and this would put us around 600. So let's label these by 100. Alright, now that we've got everything labeled, we're going to look at Part B. Part B is going to ask us to draw a linear model. Now, warning, it's a common error to try to find a line that contains the greatest number of points. Our goal is to find a line that comes close to all of the points, but it does not necessarily have to pass through any of the points. So what you're going to want to do is grab a ruler if you have this on paper. I'm going to try to use the line tool in my software right here. And I'm trying to imagine what this might look like. So I'm tracing with my imagination right here to see what I can get. Let me try to draw a line here. There we go. So the line I've drawn might actually be a smidge high. Let me see if I can go ahead and grab that to move it down just, there we go, I can move this a little bit. Okay. Because what I want to have is a line that's going to be very close to as many points as possible. So there's a point right here that's a little bit above the line, but there's 2 or 3 points right here that are a little bit below the line. I want my line to fit the middle of the data, but I'm not necessarily concerned with connecting any points in particular, just trying to center my line in the data. Now it's also a good idea if I can get this line to go longer, so let me go ahead and extend that all the way to the end of the graph. Alright, Part C. What would the model predict as the amount of money spent on cell services in 2000? Since t is years since 2000, what we're going to be looking at for 2000 would be a t value of 0. So a t value of 0 looks like it's going to correspond to about 100. Now, my line is probably crossing right here a little bit above 100. It's hard to say how much above 100, perhaps 110. See, the difference between 100 and 200 is such a short distance that it's very difficult to tell, so I'm going to estimate 110. Now, as I'm reading this a little bit more carefully, I seem to see something missing. This is the amount of money spent annually, so $110 does not seem like an annual cell phone bill to me. But if I look back up, it seems that this problem might be missing some information. It's the amount of money, but it doesn't tell me if it's in thousands or millions or what the units on this are. So I'm just left with 110 as my estimate. I'm not actually sure if that's supposed to be 110,000 or 110 million or whatever. So 110 units. When would the model predict that people in the U.S. spend about $800 annually on cell phone services? Okay, so the 800 value, it's a good thing I extended my graph because the 800 value is going to push us out to about here. And that's going to put us in between the values for 9 and 10. So what do I choose? Okay, do you round to 9 or to 10? What year would that be? So this corresponds to the year 2009. This corresponds to the year 2010. This entire gap right here is in between January 1st, 2009, January 1st, 2010. So anything in between these two spaces is in the year 2009. We have not yet hit the year 2010. So my answer must be in the year 2009. Let's take a look at the next page. The next page has two definitions for us, interpolation and extrapolation. Interpolation is when you make a prediction that is in between two known data points, and extrapolation is when we make a prediction that's outside the data points. So we're going to go back to the previous graph and label the areas of interpolation and extrapolation for the cell phone services. Alright, so on our graph here, we can see that our data sets are between these set of values right here. So any values between 1, 210, and 7, let's like about 600, would be our interpolation. And any values or predictions made past, whether it's past on the left or past on the right, would be extrapolation. It's important to know whether you're making an interpolation prediction or an extrapolation prediction, because interpolation predictions inside the data set, have a higher chance of being accurate than the extrapolation predictions. The further things go out, the more likely that our data is no longer going to give us a valid prediction in either direction. So, in part C, we were making a prediction based on 0 that was outside the data, so that was an extrapolation. Also, in part D, we made that prediction over here at 800 that was outside the data, that was also an extrapolation. While these are both extrapolations, we can say that because this one, the one at t equals 0, was so much closer to the data than the one at 800, much larger distance to the data, we're more likely to have a reliable prediction for that shorter distance. Alright, let's look at example 2. The percentages of materials that are recovered for recycling are shown in the table for various years. And we're going to make our own scattergram this time. We want P to be the percentage of materials, T years since 1990. So again, years are listed, but my T values are not. So let's go ahead and make a list of our T values. 1994, it's been 4 years since 1990, 6 years, 8 years, 10 years, and 11 years. The percentage that's been recycled is going to depend on the year. So we're going to use percent as our dependent variable and T, time, as our independent variable. A good scaling system for T would count by 1. These values are all close to each other and near 0, so it's going to count by 1. And we're probably going to need to count by 5s to get all of these to fit in, maybe 3. Let's check this out. If I count by 3, I should be able to get to 30. So a system that counts by 3 will fit on a grid this size. Let's go ahead and label those. Alright, and once we have them labeled, we're going to go ahead and graph all of our ordered pairs. When all 5 ordered pairs are graphed, it should look about like this. And let's go ahead and connect them with the best line that we can. Okay, this line looks decent. It's sort of centering on the data, a little bit above and a little bit below. It kind of tries to fit the middle. So let me go ahead and extend it so that it goes all the way past the ends of my chart here. Alright, so we've got our scattergram. We've drawn the line that comes close to the points. And the next page is going to be some questions about this. The first question is, use the recycling model to predict the percentage of materials that will be recycled in 2011. Let's go back and look at that graph. So since we're talking about t years since 1990, 2011 is going to correspond with a t value of 21. Let's see if I can see a t value of 21 up here on my graph. I need to make my labeling a little bit longer here. Alright, 21 is going to be just past the edge of my graph right here. And so I can imagine that 21 is going to be along this line. My line is not quite long enough, so let me go ahead and extend that. When I extend it, I believe that the value for 21 is going to be about here, and that's going to, again, my scaling right here is a little bit small for this particular question, but it's going to correspond with the next highest value up here. So 33, this would be 36, this value would be 39. It's hard for me to tell if it's going to be right on 39 or if maybe it was at 38. I can't make a very good prediction when my scaling system caused the values to be off the grid. So we'll do our best. In 2011, we predict that about 39% of materials are recycled. Using recycling model, estimate when about 1/3 of materials were recycled. 1/3 or 33%. Let's go back to the graph again. Alright, 33%, 1/3. So it's going to occur right here. It's going to correspond with 14. Okay, so let's go back to our answer sheet. A t value of 14. Remember that we're counting since 1990. So a t value of 14 is going to put us in 2004. In 2004, about 33% of materials were recycled. Let's talk about some errors in estimation. It's common to confuse the meaning of data points and the points that lie in the linear model. The data points are the accurate descriptions of the situation. The points that lie in the line may or may not be an accurate depiction. The error in an estimate is the amount by which the estimate differs from the actual value. To talk more about error, let's look at the following example. Use the model to estimate the percentage of materials that were recycled in 1996. 1996 is going to have a t value of 6. So in 1996, with my t value of 6, the model puts us right here. That's the spot where it intersects with my line. And so we would guess that would be about 26. Now here's the difference we're talking about. The actual value is this data point that we can see in the chart. The actual value is 1996 corresponds with 27. That is not the prediction that the model gives. In this particular place, the model is a little bit lower than the data. The model gives a different predictive value. So there's some error in what the model tells us versus what the original values tell us. So the model predicts about 26% materials recycled for 1996. Is this an underestimate or an overestimate? This is an underestimate because it is a value that is lower than the value that we know is correct by the data. Calculate the error in the estimate. The error in the estimate is the correct answer minus the predicted answer. So the error is 1% difference. What does it mean if p equals 100? Okay, if p equals 100, we're talking about 100%. The units on p are always in percent, for this case here. 100% means all materials are recycled. Can p be greater than 100? Since p has units of percentage, p cannot be greater than 100. You cannot have more than 100% of something. Now, from what we know about lines, we know that the line that we drew is going to continue on forever. It will eventually pass 100%. We're going to have a spot. Where it crosses 100% and where it goes above. Anything above 100% is impossible, so that's going to be a model breakdown. A model breakdown is a point where the model gives a prediction that makes no sense. This happens especially often with extrapolation, when you're far from the data set. Most data sets will have a point after which they no longer make sense.